Welcome to Thermodynamics Screencast number 3 for Chem 1B at Shasta College. In this screencast, we're going to take a look at the meaning of Gibbs free energy and the meaning of Gibbs free energy change. We've been doing lots of calculations. We've talked about spontaneity, but there's a few other things that should be mentioned as well. And one of the ways to look at Gibbs free energy and Gibbs free energy change is to realize that the standard Gibbs free energy of formation, delta G sub F, is the free energy for the reaction forming the compound from the elements that make up that compound in their most stable form and under standard conditions. And here we have some free energies of formation for some compounds: water, silver chloride, ammonia, hydrogen iodide, nitrogen dioxide, and benzene. And let's take water, for example. The delta H of formation of water is negative 237 kilojoules per mole. And what that means is when water is formed from its elements, hydrogen and oxygen, 237 kilojoules of energy, of free energy, is given off or released. Similar idea for silver chloride and ammonia. Both have negative free energies along with water and free energy of formation. And in general, if the delta G of formation is less than 0, what that means is the compound that was formed is thermodynamically more stable than the elements from which it was formed. So energy was given off when the compound is formed. Therefore, the compound is more stable than the elements that made it up. Now, conversely, if we have a positive delta H of formation, then the compound is less stable thermodynamically compared to the elements that made it up. So, for example, benzene takes in 124 kilojoules of energy to make a mole of that from carbon and hydrogen, and it's therefore not as stable as the carbon and hydrogen by themselves would be. And then one more thing to note, of course, 0 is the delta H of formation of any element. If a compound happened to have a delta H of formation of 0, that would mean it was equally stable to the elements that make it up. And of course, elements themselves will have a delta G of formation of 0 because to form the element in its most stable form from the element in its most stable form doesn't require any energy to do that. So there's one way of looking at Gibbs free energy change, specifically with regard to Gibbs free energy change for the formation of a compound and its thermodynamic stability relative to the elements. Now, a second way to look at this is the Gibbs free energy change is the amount of energy available to do work from a given process, the maximum amount of energy that's available to do work. And maybe an example, we go back to the gummy bear reacting with potassium chlorate and forming carbon dioxide, water, and potassium chloride. And the delta G for that process was about negative 6,700 kilojoules. It's a negative value, so energy is given off. Free energy is released when this process occurs. And the 6,700 kilojoules of energy that is released is available or free to do work. So there's where the free energy change term comes from. Not that the energy is free as in it doesn't cost you anything, but that the energy is free or available to do some work. Note also, we wouldn't say negative 6,700 kilojoules is available, because the negative here means energy is released or given off. If energy is given off, then it's available to do something with. So we would state this as 6,700 kilojoules of energy is available or free to do work from this process. Now, it's also worth noting that we won't be able to get all 6,700 kilojoules to do work. Some of it's going to be wasted as heat or some other form and not turned into work, but that's the maximum if everything went perfectly. And then one more way to look at delta G, remember it's the criterion for spontaneity. We've talked about this a fair amount. And delta G being negative for a process means the process is spontaneous. So if we're at constant temperature and pressure, then the direction of spontaneous change is the direction of decreasing G. So if delta G is negative, then that means that if G itself goes down, if it decreases, that's how we get a negative delta G. So for a generic reaction, reactants make products, we often draw free energy graphs that look something like this. On the y-axis, we do free energy, higher free energy on the top, lower free energy on the bottom. And then on the x-axis, we do the progress or course of reaction, starting with reactants on the left and products on the right. And here we're starting with reactants that have a higher free energy than the products. And then just as a note, the equilibrium position is typically somewhere between reactants and products. Some reactants could essentially 100% make products. Some reactions might have the reactants not react at all. But in general, the equilibrium mixture is somewhere in between. Now, we often make the analogy to free energy and the equilibrium position of a reaction and a ball rolling down a hill with an equilibrium position in the valley. So if we have a rock up here on the top of the hill, if you give it a little bit of a nudge, it will roll downhill without any continuous input of energy after possibly the little nudge to get it started. And where it will come to rest is in this valley. Now, if you had started with the rock over here on the sort of product side, so to speak, of the valley, it would roll downhill to the left, but still come to rest in the bottom of the valley, which is the analogy for our equilibrium position for a chemical process. So a couple things to note. Note that the position of equilibrium, the bottom of the valley, is a minimum free energy value, and it corresponds to a delta G being 0. And people who are familiar with calculus and slopes being related to derivatives notice that at the bottom of this free energy curve, that's where the derivative or the slope of the line is 0. And if we have a closed system, reaction is going to continue until we reach equilibrium, and reaction will occur in whatever direction it takes to decrease free energy, and it'll continue until the minimum value of free energy is reached. And notice these are free energies, not changes in free energies. So if we start here with quote-unquote full reactants, the reaction goes in the direction of decreasing Gibbs free energy G until it reaches equilibrium at the minimum value of Gibbs free energy. And if we had started with substances in the quote products form, then it would go in the direction of decreasing Gibbs free energy the other way until it reaches the equilibrium position. And this is going to happen whether the reaction is product favored, which would have a negative delta G. So notice, here's the free energy of the reactants, there's the free energy of the products, and delta G is a negative value because G itself decreases. And if we have a reactant favored process where delta G is positive, then here's the reactant's free energy. The product's free energy is higher, so the G of the products is higher, so delta G for the reaction is positive, and the position of equilibrium is closer to reactants. And in either case, the reaction will go in those directions. So that's the end of screencast number 3.